guess you have to please yourself because there are a lot more coming next week. But we're giving you two-day break, Saturday, Sunday. So. And partly for that reason, and partly actually, that's why if you look at my talks, they all seem to be so easy. All the problems get solved right away, one after the other. And, so the idea here, sorry, yep. Hold on. Okay, so the purpose of my talks are basically that some of you are new to inverse problems or are thinking of getting into problems. My goal is to show you different types of inverse problems, a little bit of where they originate, what the inverse problems are, a few of the results, and maybe a little bit of the idea of the techniques. So I haven't really been going much into the techniques. Okay? Little bit I have been, like the exponential solution for the elliptic case, for the transport equation, the singular part, breaking up to U0, U1, and U2. And then I'll show a little bit here for the hyperbolic case. But really, I've not really been going into the details. Some of those things are difficult and, require effort. So that's my motivation. We've been through the elliptic problem, we've seen transport, and I was showing you hyperbolic. And we were doing the one-dimensional problem. And I want to show you that one-dimensional result because that is as complete a result as I've seen for an inverse problem, for a nonlinear inverse problem for a PDE. Right? Okay. So let me just go back and show you that result, or talk about that problem. Right, okay, and I want to, I went through that scheme and I was saying it's a fixed point problem and all that stuff. Let me try to tell you about the same thing in another way, all right? And it's a little easier to understand that way also. So the problem was this, that, think of this as the mouth and this as the vocal tract. Okay, this is the same thing as actually think of this as the surface of the earth and this is inside the earth, the depth. I've turned the earth sideways here, okay? So it's the same whether you want to think of earth and, that's the surface of the earth where you can do measurements. You're trying to know what's underneath, where there is oil, where there are diamonds, whatever. Not diamonds, but oil is diamond, I guess. Along like that, think of this as really the earth, the depth, okay? So what you do is you put a source there at the mouth, you set off an explosion, and you're taking pulse measurements right here, right? And so you're doing everything here on one edge, and you want to say everything inside here, right? Of course, you're not going yourself inside. What you did was you sent a sound wave inside. And that's why you're able to say something about the inside. So all these inverse problems we've been doing, we're always making measurements at the edge, trying to say something about the interior. Okay. So source and receiver are at the edge here, same location, right? This is very important, at the same location. Okay, and this was the problem. So U was the solution of the wave equation, except there was this coefficient sigma of x, which represented for there's a place here if you want, there's one right there. So sigma of x in the case of the vocal cord problem represented the area of the cross section. If you're thinking of the earth situation, sigma of x might be some sort of measure of density or something at the point x, right? And different values of sigma x, there is oil here, there is water here, there is rock here, whatever. Okay? So, and this is the physics. U is the pressure, and how does it interact with the medium is through the wave equation. And it is true for the half line for all time. This is the model for the source. The ux at x equal to 0, that's at the beginning, is delta t. It's very important in hyperbolic problems to use delta sources. If you do not use delta sources, you use some smooth functions. And if you use only some of them, you'll not have enough information. Engineers understand this very well. You need to excite all frequencies. If you don't excite all frequencies, you will not be able to recover your whatever object. You'll only get some partial information about the object. So that's why, if you notice, for all the hyperbolic problems I'm going to do, I'm going to always use delta sources, which is explosions. Okay? And nothing happens in the earth or your vocal tract before the explosion, right? It's all quiet. So, this is an initial boundary value problem. Okay? And the goal was so this was the source at x equal to 0, and my receiver is also at the origin. So you measure u at the origin. That's your data. And question is, can you determine sigma x, whatever the acoustic property is? Okay. So I gave you a scheme, and let me explain it to you another way, right? So these problems actually you can also study in the discrete setting, right? Instead of the earth being one continuous varying thing, think of earth as one layer here, then another layer, another layer, another layer, another layer, right? And between two layers, so this is constant here, something is constant, there is what I call, just a made up term, a reflectance. So what you're trying to do is, you're trying to recover the reflectance at each interface. So it's a discrete problem, right? Let's think of it like this. So you have, this is a space-time picture, this is the space picture. There are layers, constant in each, and there is a so-called reflectance across each layer. And I'm trying to recover the R's. R is like the sigmas, but okay, that's the goal here. Now, what is the replacement for the differential equation in the discrete case? The physics actually is captured by this is the physics. So this is the physics here. So suppose you have a layer R, layer with reflectance R. So if a signal of strength 1, this is in space and time, right? Space here, time here. This is a signal moving in space and time. It comes here, hits 1. If the reflectances are 1 minus R will go this way and R will go that way. That's what happens. Okay? And if but the reflectance, it's related determined by some constant value here and constant value here. So it's not the same from both sides. When you come from this side, the reflectance is minus R and what goes through is 1 plus R. That's the physics, and you can connect these two actually. So as far as the discrete problem is concerned, you can forget about this and just think this is your physics, this is the replacement for that, and this is what is happening here. Okay? So what you do is the thing is that you send a signal 1 here. You start with 1 here, it hits the first interface. Correct? So 1 minus R1 will go through, and R1 will come here. Then this 1 minus R1 will come here, it will go 1 minus R1 times 1 minus R2, and 1 minus R1 times R2. Okay, and when it comes here, it is fully reflecting. I'm forgetting exactly. I think so this R1 came here, I think that you send back R1, or minus R1, okay? That's what this implies. Actually, it's fully reflecting here. Then it comes here and it goes. So for example, so this is where you're making your measurements. You are on the surface of the earth, time varying signal. That's what you're measuring. First thing which comes back is R1. What comes back next here? This is R1, 1, R1, then this gets reflected and this gets reflected. So this thing is experiencing contribution from 2 things. This thing will experience contribution from 3 things. And as you go higher up, the next thing will experience the interaction from 4 things and so on. And you can actually explicitly write it down what it is. Okay? So this is the forward problem. You give me R1, R2, R3 and so on. I can actually tell you what will show up here. Right? You can write an expression. These are algebraic expressions. Polynomials in R1, R2, R3. And the inverse problem is, I give you these polynomial expressions. Can you tell me what R1, R2, R3 and so on? That's the inverse problem. Right? That's exactly what I was trying to do here, but so this is the physics, that's the replacement for the differential equation. So this tells you how this interaction will work here. And the inverse problem is, I know what's coming here. Just a function of time means that this. Can you tell me what R1, R2, R3, and so on? Okay. And it's very easy to understand the so-called scheme that Gelfand-Levitar time scheme with this way. Right? And you'll say, it looks so simple, why is it so hard of a differential equation? Okay, some things are simple, but that's really what I did actually. When I was telling you doing that, fixed point and small steps and so on. This is roughly what I was doing. Okay, so let's look at what we measure. The first thing we measure here is R1, right? So just from that itself, I know the reflectance of the first layer. Just from that itself, I know the reflectance of the first layer. Now I know this, and I know R1. I claim because of this physics, because I know R1, I can get the values of all these things on this layer. So this is the sideways step. When I was telling you, I can go sideways. The sideways problem is well posed. Because of the role of x and t is reversible, that is what this step is. If I know R1 and I know this data, I can move it all forward. That is the sideways step that I was talking about. You can only do this in one dimension, because in one dimension, the suppose role of x and t is reversible. You cannot do this if you had a Laplacian here. That is the one big difference why multidimensional problems of this kind have not been solved. Okay, it's the 1D problems which are solved here. So this sideways thing is because the role of x and t is reversible. That's sort of what's going on here. So I got R1, and I have this. I can move this whole thing forward, and I have this information. So now something is going here. I know what that is actually. It's 1 plus R1, but I don't need to know that. What is coming back here? Whatever is coming back is exactly R2 times this. That's it. Whatever went in here, what came here, this is going on. What is coming in here is R2 times what went in here. Okay? So just from that reading, I can figure out what R2 is. Okay? Once I know R2 and I know this, I move it forward. Again, what comes here first thing is R3 times what went out. I know this and I know that. So I can get R3, move forward. Okay? And that's the algorithm. Okay? So it's the same thing which we were, so it seems so simple, but that's exactly what is happening in the continuous case. Right? So what is playing a role is, which is the role of x and t is reversible. You can move. What about this part here, that you can figure out R1 from this? This is where I was using this aspect. What aspect? Remember this thing here? Sorry. Yeah, well, in some sense. This aspect here, okay, is the thing that I can read the first reflection. That's what this is. Okay, this is sort of the equivalent of that when you do the algorithm. Okay, that I know the value of u on this boundary, which is sort of, that's exactly what it is as the first reflection part. Okay, so okay, so this picture here, this was done by the way, I think a person called Gopior, I think. I mean, this is called a Gopior medium. This the piecewise constant approximation with fixed depth and fixed velocity. It's GOUP, Gopior medium it's called. But actually here also, this is a little non-trivial. Okay, so, okay, I've shown you the inversion, right? But the question is, by the way, these values of R are numbers between -1 and 1. Straight, when you do this physics here, these R's always are real numbers between -1 and strictly between -1 and 1. Okay, so you can ask questions like, what is the possible sequence that will arise? Right? What is the range of this thing? Right? For different sets of R1 through Rn, any choice of R1 through Rn between -1 and 1, what are the possible sequences that can arise? Okay. Now, so what data can you write? Now, instead of writing this as data, you can write it as a polynomial. This is the coefficient of 1, this is the coefficient of z squared, this is the coefficient of z cubed. You can represent the sequence as a polynomial. It's a question of what kind of functions, polynomials can arise from such things. Okay? And when you go and try to do all this, this actually leads to a very nice complex analysis. There's a connection, I mean, this whole thing is actually a connection between, what do they call this, Stieltjes problem, between, if you have a measure and you know all the moments for that, can you recover that? This is all very closely connected to these things. So there is a very close circle of problems, which I can't remember all of them, but which are very closely tied with this problem here. And the range characterization is analytic functions on the unit disk and stuff. There's a very close connection between all these different areas in this problem. Percy, Dice, and Trubowitz and stuff, and they've done a lot of this stuff, and this person at Caltech, I forget his name now, Barry Simon. So he's worked on these things, and very close connection between some issues in complex analysis, Stieltjes integrals, and all kinds of things like that, which I don't know so much about it, but there are very close connections. Okay, so I want to talk about now some other problems. So source and receiver at this location, right? Sometimes, for reasons which I'll not say right now, sometimes what happens is you have your source here, and the receiver is not here, but somewhere here. That's where you're doing your measurement. You're not doing your measurement right away. You do your measurement somewhere else, for whatever reason, but let's say. And that leads to a slightly different kind of problem. Okay, so let's say I'm doing a problem. I mean, this doesn't make sense for the vocal part, but some other problem. You put your source at that end and the receiver at that end. Okay? And then same differential equation, same physics, your source is still right there. But what your data now is different. Right? I'm assuming that the medium is uniform after that. So sigma x is 0 after this capital X. This is capital X. Okay? Now I give you information u at this point. Can you tell me what sigma fx is? Right? Okay. So this is a different and a little difficult problem. So this was, in the discrete case, was done by Claire Wu and I and Paul Sachs in 1996. Let me explain to you why it is different from what we just done before. Okay, and what's the difficulty? Oops, sorry. Same physics, right? Same layers and everything, right? So let's say there were only 3 layers. Okay, so I set up a delta function. This source here means you send a signal of strength 1. That's all it means. It means you send a signal of strength 1. Anywhere else, it's fully reflecting. Whatever comes here goes back. Whatever comes in goes back. Whatever comes here goes back. That's all it means here. Fully signal 1 here. Okay. And where are your measurements? Your measurements are here. Okay, let's say there were only 3 layers. Okay, your measurements are here. And you're still trying to get R1, R2, R3. Right? So what's the first measurement, right? 1 goes 1 plus R1. This goes 1 plus R2. So 1 plus R1 times 1 plus R2. 1 plus R1 times 1 plus R2 times 1 plus R3. Am I correct here? Right? 1 with that physics. Sorry, 1 minus. Sorry, 1 minus with that physics. So 1 minus R1, something goes here. Then 1 minus R1 times 1 minus R2 from that physics. And then 1 minus R1 times 1 minus R2 minus 1 minus R3. So what information did you find out after the first thing? You couldn't get R1, you couldn't get R2, R3. It's all 3 are mixed up. Right? Unlike here, where the first thing would just give you R1 right away. Okay, so you say, well, maybe if I take the ratio of these 2, I'll get R3 right away. Right? This one was straight coming through. What is coming here? Well, you go like this, and like this. Or you go like this, and like this. Or you go like this, and like this. So this also could be a sum of 3 different reflections and then transmission. So the ratio of these 2 is not going to come from R3, give you R3. It's really a combination of also R1, R2, R3. So basically what you can't do is, just from the first one, figure out R3, then move in, and then figure it out and then move in. You can't do that. It's not easy to extract from all this the information about any one of these individually right away. Okay? So this problem here, where the source and receiver are at different locations, is very different from having the source and receiver at the same location. Because you cannot do this scheme of, well, get that, get the first reduction, move forward, get the second, right? You cannot do that, right? So we solved this, well, Claire Wu actually had suggested already a discrete idea, which is, when you take this information, you can construct from it some other data by doing some inverses and stuff, which apply to a problem like this. It sort of corresponds to having data here. So the tricky bit is from this, how do you extract that other that information to which it applies to a problem like this. Once you have that, then you can repeat it. So that step is needed in between. From this information, how do you get some other information to which this kind of thing can be applied? All right. So the model from this is that if source and receivers are in the same location, then this kind of trick will work through, at least in one dimension. So this is what I call, if source and receiver are at the same location, you send this, come back. I call that reflection data. When source and receiver are at different locations, it's transmission data. It has to go through the whole thing before you see anything. So whatever you see is mixed up everything. Whereas source and receiver at the same location, the first thing you hear is only from the close by. Later things will come from above. Okay? So this is actually a principle which plays a role throughout this hyperbolic inverse problems. Okay. So here is, many people who know about inverse problems for hyperbolic think, everything in 1D is on Gelfand-Levitan, everything is solved. Here is one problem which is not solved actually. I've tried to do it and I tried the other trick, but it hasn't quite worked. So it's an open problem. So which is that you have a medium, let's say, and it's uniform outside. Okay, it's not a practical problem. It's actually a sort of a problem which motivated by something in 3D. Okay, you have a medium which is constant outside, and this is the part which is unknown. And some of the source is in the middle, and you have receivers at the ends. And can you determine? So you notice that this is the transmission, right? This is sending stuff here. And this is also sending stuff here, which might get reflected and come back. Might go there and come back. And some stuff is also going there. So what this is getting is all mixed up from both sides. Okay. And so I'm calling this x, and this is cap minus x. So same wave equation. This is the source in the middle at the origin. And before the explosion happens, nothing is happening. That's the initial condition. Okay? And the data, sigma x is 0, meaning outside this, it's all just the standard wave equation. So you don't have to worry about that. And given the value of u at the two ends, can you determine sigma x? And there's a discrete version of this, the Gopion medium, so even that is not solved. Right? So in fact, before you solve this problem, it's better to work on the discrete version. If you can solve the discrete version, you can sort of figure out how to do this. So you can set up the same layers and do that physics and figure it out, and work with polynomials rather than functions. But I haven't been able to figure it out yet. Okay. Now let's go to multidimensional problems, hyperbolic problems. Okay. I took this from the web. So I think it's a JPEG picture. It's supposed to be smaller, and then you see it more sharply. But I expanded it so it doesn't look. So this is supposed to be seismic imaging, right? As Guy was saying that there were people going around in Dallas. They were wanted to put things on receivers in there, and so they could set up an explosion. This is sort of what it is. I'm sorry it's very hazy because the picture is being expanded. Okay. So what they're trying to do is trying to map what's underneath the earth. And this cartoon is Chevron oil. They push it. It must be correct. So what they have is, so there is a truck here, and it's going to thump the ground or do something. Okay, very hard. And they have set up these receiver stations on the surface. Like it pulls it. It's a truck which is attached to these things, and it's going to. So when an explosion goes, think of this as the layers of the earth. It's coming, the sound signal is coming, it's hitting this, it's going there, it obeys the law of reflection, actually. The first scattering. Okay, comes here, it goes there, and so on. And so these they record, and so they know the locations of these things, right? They know where the source is, where the receivers are, and they'll do a record over time. And from that, they want to know what's in the layer here, right? So this is some acoustic property of these layers, and from that, I believe, I don't know this very well, but certain structures will trap oil or gas. They have to have the right shape and stuff, and they will trap oil and gas. Otherwise, the gas will diffuse. Even if the gas is in that area, if the structure is not right, it will diffuse and just go away. Okay, that's what I've heard people say. I don't know much about these things, but okay. So this looks like wonderful. All this information is coming in, and go ahead, just solve it and cover it. And it's the wave equation. But we'll see there are some issues here. And one issue comes up right away, okay, which is not shown in this picture, but they are very well aware of it. Is this, okay? So you set up your source, okay, and by the way, what happens is, so they'll do this mapping, and then they'll move this 100 meters or 10 meters and do this, and this will pull, and then do it again. So what is really basically, you can put your sources all over the place and receivers all over the place. Essentially, that's what you're doing. Right? You did this source, all these receivers, move it, do it again, move it, do it again. I think Cliff Nolan is going to talk a little about this, okay, about this combination of sources and receivers. But roughly that's what's going on. Okay, there's something here which already tells you this is, forget all the mathematical difficulties. It already you can see something that there is not going to be enough information. Okay, and here is why. So you set up your source here, and suppose this is your layer, right? You send the signal there, right? Now this is Professor Bowman's wavefront set here, right? Suppose there's a layer here, there's an interface, right? So the function, the whatever coefficient recovering has a discontinuity in this. And what is the direction of the discontinuity? That's the wavefront set there, okay? The normal to that surface captures it. So when a signal arrives at this is you can prove mathematically, so for the wave equation and stuff. When it arrives, it will be reflected. It obeys the equal angle law of reflection with the normal. You can prove all this rigorously. Okay? So what happens to this? Where is this headed? Nowhere to any of the receivers. If you move your source here, okay, it'll go a little like that. If you move your source here, it'll go there. So if the interface is more vertical, no matter where you put your thing there, this thing is never going to reach the thing. Right? You have to do it maybe all the way here. Like if this is the normal, you put your source here, then it will go and come. But then this is so close to the earth, but you have to go so far away to it, right? So which means that you will have trouble. This may not be in your data. This information is not coming to your data. Which means when you're trying to do inversion, you will not be able to recover such interfaces. And which is when you're trying to do mathematics, right? You will not be able to recover the Fourier transform of the function in these directions. You will not be able to estimate it. So this already tells you that when you're going to study these inverse problems mathematically, with sources here and receivers here, you will not be able to estimate or do anything with functions which are like this. Okay? So this is already a problem here. So as mathematicians, we want complete results and the nicest results. So you say, well, what is a problem in which this issue does not arise? So that's what I'm going to study. Okay? But if you're an engineer, you're a real person, you have to go and deal with this. And if you can't do it, well, you have to find some way of doing it, right? So that's why, sometimes what engineers do is pretty hard. They do all the hard stuff. Mathematicians think, oh, it's too difficult, let me try something easier. This is not there, it's not there. You have to deal with it, right? But we are okay. Well, you don't expect a theorem, but you can. So you can create a theorem and say, well, what is it that you can recover? You can write theorems like that. What is it that you can recover? And that's important, right? But if you want the theorems in the nicest form, not without 500 conditions and so on, then you try to make your problem simpler. So how can you make your problem simpler instead of doing this? What was missing was that you didn't have receivers all around. If you had receivers all around, you'd be okay. Of course, in the earth you can't do it, but in mathematics we can. So that's what we were going to do. So I'm going to do a problem where sources and receivers are all around. Okay? So this is my domain here. This is my earth. Of course, in if you think of the earth, then this is somewhat feasible, right? Of course, but you cannot put receivers all around the world, right? In certain locations you can. So here is my domain, some acoustic domain. And what I'm going to do is I'm allowed to put my sources on the boundary. So this is supposed to be the boundary. Okay? Put a source somewhere on the boundary, explode, measure the signal everywhere for a certain time, move my source, measure the response again everywhere. So I'm allowed to move my sources and receivers, but always on the boundary. Okay? So here is the physics of everything. So there is some so-called acoustic pressure. This is all a cooked up problem. Okay? It's just a way of thinking, but the real problem's got nothing to do with actually what happens. Okay, so D is the region in R3, Ux is the pressure at point x at time t, and Q of x is whatever acoustic property of x you're trying to recover. Okay, and the physics are, and Qx is 0 outside D. I'm going to assume I know everything outside and it's just standard constant. Air or whatever, just, okay? And the physics is, of course, I've changed the differential equation a little bit, okay? I put it on the 0th order term. You can do this, you can try to work, okay? And this is my source. Where is the source? Source is located at time 0, the explosion happens. Source is located at point A. So point A is here, outside, or on the boundary, if you like. Right, remember? So this is my source, and I'm going to move my source A around here. Okay? And before the explosion, nothing happens. So this is an initial value problem for the wave equation. So if you give me the Q, you tell me where your source is, I can put it on my computer and solve it as well, posed and everything. The inverse problem is, I give you the value of this solution at the receiver. So I give you U xt. Well, the solution is dependent on where the source is. That's why I'm putting the A here. But it's just U xt for all x on the boundary. And for all source positions A on the boundary. And for all time. Can you determine U? Right? So let me repeat that, okay? So the solution U depends on where your source is, because it's showing up with the A here. Okay. So I have U of xt. So my data is U xt, x on the boundary, A on the boundary. Okay? And determine Q of x. So as usual, first thing you do is do parameter count. So how much data do we have? I know for every x on the boundary, that's my receiver location, this is my source location. So this is all in R3, by the way. Okay, I'm doing it all in R3. X is on the boundary, so boundary of a three-dimensional thing is two-dimensional. Source anywhere on the boundary, two-dimensional, time 5. What is it I'm trying to recover? Q of x, 3. So it's an overdetermined problem. Sources and receivers all around. Okay, so it's an overdetermined problem. And that's why I'll be able to solve it very easily. Okay, so let's see why. And actually the idea I'm going to sort of show you here is the same thing which we use in the transport problem. Okay, which is what I'm going to do is, I'm actually going to try to write down the solution U explicitly. Now, as you all know, right, if you have any differential equation with non-constant coefficients, you can't really write down the solution. So, but you can get some features of the solution. And those features, just like in the transport case, will be enough. Okay? So, that's my differential equation. My source is at A. Okay, and this. So, that's my problem. Okay, this is where my source is. This is for space-time. So this is where the explosion happens. Notice that it's a wave equation with speed 1. If this is where the signal happens, there's nothing happening before that, well then your solution is all start with speed 1, right? So your solution is actually non-zero only in this cone, space-time cone, 0 all the way before that. Okay, so really everything is happening here. So what is the solution? If Q was 0, if the medium was uniform, that is just the what is called the fundamental solution of the wave equation. And because it's a 0th order term, the solution is actually the fundamental solution plus a perturbation. What is that perturbation? It's some function U of xt. So this is the fundamental solution of the wave equation, which is if Q was 0, then that's the solution of that, plus some U. Okay. Now this U is 0 here, and it's supported inside, right? So I don't really know much about U, other than it's actually a solution of the same equation. But the fact that it's the delta function there allows me to tell me the value of U on the cone. Exactly on the cone you can write down. This is very standard. I don't know the value of U inside, because but just on the cone, because it's a delta function, you can actually explicitly write it down. Let's see if I wrote it down. Yeah, there it is. Okay, and I'm trying to explain in words what it is. This doesn't take any great mathematics, it's just so-called the progressing wave expansion. This has been known for 70, 80 years. Okay. So I don't know the value of U inside explicitly, but I can tell you what's the value of U on the cone. And what it is on the cone is, so you want to know what is the value of U at this point. What you do is drop down in space. Okay? Look at that line segment joining A to X. X is that point. Compute the integral of this coefficient Q of X on that line segment. That's the value at this point. That's what I've written here. Okay? It's the integral of Q along this line segment. So the solution capital U is the singular part plus something smoother, which is supported on the inside. I don't know the exact thing inside. What I do know is the value on the characteristic cone. Anywhere on the characteristic cone, you want to know the value, project it down. It's the integral of Q. Q depends only on X on that line segment. Okay, this is just standard expansions you can do. So let me write it. So what I can do is, say, what do I know? Right, okay. Let's go back here. So this is the solution. What is the information I have? I have U of xta for every x on the boundary, t all time a on the boundary. That's what I have, right? So I'm going to, and this doesn't carry information about Q, so I'm just going to work with this because I can separate the two. Okay, this I can separate. You can pull out from anything. This is a known quantity, so if you measure anything, just pull it out, right? So here is the new problem. Okay, let's see if I do this. Okay, yeah, let's come back here. So I know I'm given UXTA, which is, I'm given this. I think I missed a slide, or let's see. Right, all right, okay. So I know this information. Where do I know this? I know it for every x on the boundary, a on the boundary, arbitrary t. Right? I know this for every x on the boundary, a on the boundary, arbitrary t. In particular, I know this. So for every, let's say this is the boundary point. So I know this for every x on the boundary, a on the boundary, and all t. I'm only going to use it for one t. And I'm going to use it only at this t. You've given me so much information, I don't want it. I'm just going to use the value of t at this point. So t is absolute x minus a. That's what I'm going to do. Right? That is known to me. So if you give me this value of t, which means I know the integral of q, which means I know the integral of q on from a to x, for which a and x. For a on the boundary, x on the boundary. Those are the only ones I know. Okay? So, as I said, I'm given u of x here for every x on the boundary, a on the boundary, arbitrary t. I'm not going to use it. I'm only going to use t equals absolute x minus a. That's all I'll use. If t equals absolute x minus a, it's this integral. So I know the integral of q from a to x for every a on the boundary, every x on the boundary. That's what I know. Just that information. Well, I can move a anywhere around, x anywhere around. So I know the integral of q on every line crossing this. So I know the X-ray transform from that you can get. Seems so simple, right? I mean, if you go back here, so this case here. So basically, if you do sources anywhere and receivers anywhere on the boundary, it's very easy to figure out the integral of the unknown coefficient on all lines through this, okay? And I can move my source receivers for all lines. And I didn't even use all the information, right? Remember, as I said, I used UXTA only at t equals absolute x minus a. So this is like the transport problem where I didn't need to use everything, just that singular part. And why were we able to get away with using so little information? It's an overdetermined problem. Remember, the data depended on 5 variables as only. So that's why we could do it. Okay. Let's see. Okay, that's what I'm saying here. Okay, and here is a line which Slava. So you heard Professor Kurilov's talk here, right? So actually, the two problems are very closely related in some sense. Let me go back and show you. Let's see, what is the next slide? Yeah. No, sorry, this is not it. So I want to put in perspective what his talk was and what I've done. My problem was so simple, and he was working so hard. So maybe, he doesn't know something which I know, right? Let's see why. or vice versa, correct? So let's look at what is the difference between the two problems. Okay, his problem was this. Here is a manifold. Okay, this is equivalent to what he sort of said. Okay, so you have receivers all around, and you do something, and you send a signal, and you measure the response, and you keep doing it, and you measure this in space and time, right? And you're trying to recover the metric and the topology and stuff, right? So I'm sort of doing the same thing. I'm trying to recover what's inside, and the same physics, by the way. It's the same physics. I have the wave equation plus Q, and his also is the wave equation, but we'll soon see the differences, and they are very major. Okay, it's the same physics, same wave equation. And what he was talking about, knowing those things, is very equivalent to this. Put your sources here, receivers all around, send a signal, do it, keep doing it. And he's trying to recover the manifold, the thing, okay? So what's the difference? I could do it in 5 lines if I just do that, right? So first big difference, right? What is he trying to recover? He's trying to recover a metric, right? I was trying to recover a function Q, which was in the 0th order term. My main principal part was the wave equation. All the rays were straight lines. I was trying to recover a 0th order term. In his equation, the wave equation was replaced by the general wave equation, right, with the remaining metric. What about the rays for that? The rays are determined by the metric, and the metric itself is unknown. So you're not going to get those lines. I mean, you don't know where the lines are. Okay, so that's already a beginning. That's a start. You don't know the metric, and metric is not one function. Okay, it's a whole matrix. That's another thing, right? Then he's getting the topology and then another big difference, right? I had information all around. Where was his information? He had a small patch here, which was controlling the whole thing. If you have your receivers only here, you're not going to get those lines across. I mean, you need source here and receiver there. Then you will get all the lines, and you need to get them all around. He's just working with a small patch, which will control everything. So you can see there are substantial differences. And that's why it takes so much effort. See, my thing was, I was relying on the fact that, send the source there, receiver there, measure the integral. In his case, he has all his information, his sources and receivers are just right here, nowhere else. He can't send things across and measure it at the other end. He's sending things across, listening to it, and whatever's coming back. Just from that, he's trying to figure things out. That's a lot harder problem. So forget, first, he has very little partial information. He can't do this diagonal thing across. Secondly, the rays are not straight lines. He doesn't even know the direction of his rays. The direction of the rays are determined by the metric that he has. And he doesn't know the metric. And on top of that, he doesn't know the topology. So the amount of information is the same. It's in principle an overdetermined problem. But to really put into practice everything, I mean, it's very hard. If you don't know what the rays are, if you don't know where the characteristics are for the wave equation, it's very hard to do inverse problems for the wave equation. I mean, all the things that I'm doing, I always work with the principal part is constant, which means I know always know my characteristics. You try to do anything with velocities, which are unknown, that's a really, really hard problem. And in multi-D, even these problems are hard enough. So that's why you need to put in perspective what Professor Kurla was doing there. It's an overdetermined problem what he was doing. But the geometry becomes so hard in that. But that's why you need all those extra special techniques. And he wasn't just using this ray thing. He was actually using sort of a full information. He was trying to control things in the interior by changing things. So there's a lot of very sophisticated thinking going on in that approach. Okay. So I'm just trying to put it in perspective. Go ahead.
So suppose we consider the same problem, but replace Laplace by the Laplace-Beltrami, but suppose G is known.
Right. So, and then you try to recover a lower order coefficient.
You recover the zero.
Then you can sort of do similar things. But then it's still not an easy transform. Instead of what you,
you would still get the X-ray transform.
X-ray transform, but the X-ray transform not along lines now, but along the geodesics, right? Now, is that, you know that, right? So what is the state of art in that? Only for simple manifold. Right, so there can be, trapped areas where the geodesics do not go and stuff. So question is that if you have a manifold and you have a metric on it, and you know the integral of some function on all geodesics, between boundary points, can you recover the function? Well, there are places which the geodesic may not even go. Right? So there are issues like that. So I think the best answer is that it's for simple. Simple means?
Simple means that you geodesics go through.
All the geodesics go through. Yeah, okay.
It's almost like slightly deformed.
But is it known for simple manifolds?
Right. That's what he's saying.
Larger domains.
Larger means?
Yes, large in small, simple, unified system.
No, so he's telling. So they were. Right, so I'm not sure. Let's talk later. Okay, all right. So I hope I put in perspective, what he was doing and why he was working so hard. Right? Because if the rays are not known, if the geometry of the rays is not known, you really have to work very hard. So, okay. Let's see, I have 15 minutes. Yeah. Okay. So I'm working with constant rays. Okay? And you saw that when the rays are constant, try to determine a lower order term. If I do all sources and receivers on the boundary, I can solve it very quickly. So let's do a really hard problem then. So which means I don't want to do an overdetermined problem with constant rays. I want to do a formally determined problem where the amount of information matches the thing. Okay. So the problem was that I had sources and receivers all around. What you need to do is fix one source and just keep it at that. So I should really be putting my source on the boundary and receivers everywhere and don't move my source. Okay? Now, for various reasons, it's a little simpler to at least state. Neither of the problem that I'm stating is solved. So I'm just going to put the source in the middle. But it's not practical, I know, but it makes it easier to study. If you want, you can put the source there. It's even harder. Okay? Harder or about the same. So I'm just going to put my source in the middle. Just to study, okay? Just from a mathematical point of view. I'm not going to move my source. So this is my origin, it's my domain, my receivers are on the boundary. Okay? So what's the formal statement? Same. So physics is the same, except my source, now there is no A. Source is at the origin. Okay? And before explosion, nothing is happening. And what is my data? I know u of xt for all x on the boundary and for all time. Okay? And I want to find q of x. So of course, let's do the parameter. This is all in R3. Data, well, what does it depend on? X on the boundary, t time. So 3-dimension boundary is 2 plus 1, 3, 2, 3. So this is formally determined. Just that little trick I did before is not going to work. Even if the source was outside, suppose the source was outside like before, right? With the trick I showed you, what you would get is the line integral of q from source to the receiver. How many lines would be there? Source is fixed. You go receiver, 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 receiver. So all the lines going through that source. That's it. That's all you know. That's not going to be enough to determine q. Right? Does that make sense? If your source is fixed, you're not moving your source, you only have integral of q on those lines, and that's not going to be enough to determine q. So that simple idea is not going to work anymore. You have to buckle down and use the full information. Right? That's what I'm saying. So you just look at u of x for x on the boundary. It's not going to do anything for you. That's exactly what I said. Okay. So, this is the forward problem. So again, I do the analysis. As I said, when you do the analysis, this is the principal part and this is the part which is in the cone, right? This is the solution of the fundamental solution plus the perturbation. The perturbation because of the q. Right? What do you know about u? So u at least is supported in the light cone. As I said, nothing happens before that. I'll draw another picture in a second. And in the light cone, because this is the solution of the wave equation with this, so it satisfies with 0 on the right-hand side. This takes care of the delta. Okay? And then I told you always know the value of u in the characteristic. I'm going to redraw this and given this. Okay. So here is the problem, right? U satisfies, so our problem is equivalent to this. There is a function U in this light cone which satisfies the wave equation. The value of U on the characteristic is known. It's in terms of the integral of the coefficient. Okay? If you just know these two things and Q, this is a good, what's called a Gutzau problem. It's actually well posed. It's not one of the standard initial value problems, but there is a theory for this. It's well posed. Okay? So if you give me Q, I can determine U. The inverse problem is, given the value of U x t for x on the boundary and t, this is where the receivers are on the boundary. Can you find Q? Right? Let's look at this picture because I want to spend some time. This picture is important. This has all the information here, right? So the inverse problem that we were studying with receivers all around the boundary. Okay? So my domain D is here. This is the unit ball. I think it's the unit ball. This is the cylinder on top of it. Okay? My U satisfies the wave equation in this light cone. Okay? That by itself is not unique, so, but you need to know the value of U on the light cone, and that's the integral of Q. Remember that. You want to know the value of U at this point, drop it down, integrate on Q. So the value of U on the light cone is known, it's related to the integral of Q. So if you knew Q, you could solve this forward problem on a computer, and you would get the value of U at every point. In particular, you would get the value of U on the boundary of D. What is the, and for all time, what does that represent? This is the boundary of D for all time. So you know it on the cylinder. So here is another way of looking. So let me just spend some more time, okay? U is the solution of the wave equation in the light cone. Okay? The value of U on the cone is in terms of the unknown coefficient Q, unknown. What do you know? Your data is, you know U on this cylinder. So this is the unit disk, that's my domain. And you know the value of U on the boundary of the disk and time. So I know U on this. Can you tell me what the Q is? Okay, so this picture, there's a lot here, but so it's about solutions of the wave equation for the unknown Q here. Okay, so let's see what I've written here. All right, so how do we go about doing this? First thing is, notice that Q is 0 outside the ball here. So if when you do the integral of Q on this, the integral of Q at, right, if you want to find the value of U at this point, is, actually I made a small mistake, but it's essentially correct. It's essentially the value of U at this point. Okay, now U is known on this. So U is known here. So which means U is known on this part of the light cone. Here it's known. U is known here. U was given to you here on the cylinder. And not inside, but on the surface. And U is known on this. And in this region, because it's outside the region D, this part goes away. So which means in this part, U is just the solution of the standard wave equation. No Q is here. And you know U here and you know the U here. So you can get actually U here without knowing Q. If you just give me the value of U on the cylinder, what the data is, just from that I can recover the value of U in this area without knowing Q, just from the data. Which in particular I can determine the normal derivative of U on this cylinder. Okay, that's what I'm trying to reach that stage here. Okay, I know it's getting complicated, but okay. So U satisfies the wave equation in this whole region with a Q. My U was, and U is related to the integral of Q on this cone. U is known on the boundary of the cylinder. From that, I can get the normal derivative of U on the cylinder. Question is, can I get Q? Well, to get Q, all I need to do is to recover the value of U on this. If I know the value of U on this, then it's the value of U on this is the integral over every line segment, and I'll be able to do it. So question is, if you know U and UN, and you do not know Q, can you recover the value of U here? That's all you have to do. It's the solution of the wave equation with QU, and you know the Cauchy data here. Can you recover the value of U here? But you don't know Q, you cannot solve it for anything. Okay? So that's the problem. Okay. And this problem is unsolved. Okay, so as I said, for any higher dimensional inverse problem, which is formally determined. If you can prove a result, it's going to be a great result. So there are very few such results for any, whether it's elliptic or any other kind. Okay, there are very few such results, formally determined inverse problem in higher dimensions. No matter whether it's elliptic, transport, whatever, if you've got a result, that's going to be really difficult and very, very well known. So this is a formally determined problem. It's an unsolved problem, long time unsolved problem. So 40, 50 years it's been. Okay. So you can't do this problem, but the question is, you want to at least begin to analyze this. The first thing, whenever you're doing an inverse problem, is analyze parameter count. Okay, parameter count says you have enough information, just about. The next thing you do is what is called linearization. Okay, so whenever you want to study a nonlinear map, right, and you want to know is it injective or not, it's going to be very hard. So first thing you say is, let me find the derivative of this. Find f prime at some point and see if that matrix is invertible or not. Okay, and usually it's the origin you try. So you find f prime at 0, find the matrix and see if it is invertible or not. That's what I'm going to do here. So the simplest case is if q is 0, all this is very easy to solve. Q is 0, this will be 0, this will be 0, u is 0. So that's the base case, the simplest case. So whenever you study an inverse problem, it seems too hard, you go and try to study the perturbation of the base case. So the q equal to 0 is the base case, the solution is 0. You say, well, so perturbation from q equal to 0, let's assume q equal to q is small. And you do a linearization. Well, if q is small, then u is small. Okay, so these two are of the same scale. This is small. What about qu? It's small squared. So you drop it. That's the linearized problem. Okay? So that's what I'm going to do. I'm going to rewrite this problem without this term. This q is still here. This is so every inverse problem. Experts, please bear with me. You all know all this. New people, this is when you have a hard problem, nonlinear, linearize about the simple case and study it. Can you do that? Because that will give you some clues whether you have a hope of doing it or not. So I'm going to redo this problem without the QU term. This Q is here. So here is the new problem. U satisfies the wave equation in the whole cone. No Q at all. Very nice. And the value of U on this is related to the unknown Q. You are given U and UN on this cylinder. Can you find Q? Which means, can you find the value of U on this part here? Q is not known. So it's a problem of the very simple wave equation. You have a wave equation, unit ball, you have a time-space cylinder. You know U and UN. Can you get the value of U on this line? Just the wave equation. Right? This is the linearized problem about the origin. Q equal to 0. And this is also a little tricky. Actually, this was solved, what I'm going to tell you is by Romanov. It's not, once you see it, it's simple enough, but it's non-trivial actually still. So the question is, how do you, if you know U and UN on this sideways cylinder, how do you get a value of U anywhere? Right? Wave equation, we're used to solving initial value problems or initial boundary value problems. You know initial data and one boundary data. I have no initial data. I have two boundary data. So this is the time like Cauchy problem, right? When you're dealing with it, this is where Carleman estimates and stuff will come into play. That's why for this inverse problem, for the original, not here, but for original inverse problem, Carleman estimates play a role. Because it's about the time like Cauchy problem, where U and U are prescribed on a time like boundary, and to study them you need Carleman. But anyway, how do we solve this problem? This is just the wave equation. Well, you need, if you've studied wave equations and if you are studying enough time on it, you know something called Kirchhoff's formula. Kirchhoff's formula says, if you give me just purely boundary data, no initial data, there is still a way to write the solution. There's a formula. It says if you want to find the solution at this point, draw the light cone from there. Wherever it hits the cylinder, there is a way to write the solution of this in terms of the integrals of these two quantities on that circle. There's a formula. If you look up Courant and Hilbert, you'll see it there. Okay? So if you just know, this is, not many people know this, but this is not typically done. in the standard wave equation classroom. But there is a formula like this. If you know it on a cylinder, not necessarily even for the disk, any domain and any cylinder, if you know un on the boundary, you can get actually the value of the solution of the wave equation in terms of the Kirchhoff's formula. So I do it for this place here. So every point here, I can draw that and I get this. So I can get the value of u and ut on this disk. Okay, just like Kirchhoff's formula. Once I have u and ut on this, it's initial values, except I'm working backwards in time. But for the wave equation, forward and backward make no difference. It's utt. You can go forward, you can go back, unlike the heat equation. So you have u and ut on this, just solve it. Down here, you get u here. Once you get u here, you know the integral of q all the way, just differentiate. So this is the linearized problem, just a simple case. At least we can do it. So you know there is hope, right? But the original problem, there is no hope. And no, it's not done yet, sorry, not no hope, but not done yet. But you can see the original problem, original problem, it's really about, you have Cauchy data on the side with time lag, and you're trying to recover this without knowing Q. So you can see that, time like Cauchy problem, tools are going to play a role here. Carleman estimates are going to play a role here. Okay? But Carleman estimates are for unique continuation. You're not only doing unique continuation, you're also doing finding the coefficient simultaneously. You have to go something beyond unique continuation. Okay? This problem is unsolved. Okay. So this was the problem I was working on. I'll just take one more minute because I'm going to tell you one result which is known. And that was an important breakthrough. So my source was here and my receivers were all around. And I was trying to recover the coefficient Q. Okay, my source was the delta function, which it's gone out to this. So there's a delta function here. This is an unsolved problem. But there is a result, a famous result, because as I said, any result for formally determined problems. So instead of this source, there's a famous result of Bukhgeim-Klibanov, which said, I'm going to use a different kind of source. Instead of explosion at one point, I'm going to shake the whole Earth. So that's what is not good about that result. But the result is that if you shake the whole Earth at one time, and you have receivers all around, then you can do at least uniqueness. And this is the result. And it's very famous. They were the first people to introduce these tools of Carleman estimates into inverse problems. Carleman estimates are well known for unique continuation. They were the first ones to bring Carleman estimates into inverse problems. So here is what the result is, and then I'll stop. So D is a bounded region. You can think of it as a disk. U of x is a solution of the following initial boundary value problem. Satisfies the wave equation. Boundary, everything is, sources are not on the boundary. Okay? Receivers are there. No source. This is my source. Initially, I'm going to shake the Earth. This is my source here. And ut is 0. Right. So what is my measurement? My measurement is the value of u on the boundary, where the receivers are. Take the value of u where the receivers are for all time. That is unique enough to determine q of x if t is big enough, t is bigger than the diameter, and if ax is non-zero at every point. So you've shaken the Earth at every point initially. Right away, you shake the Earth. So that's a very, it was quite a feat, this thing is. They were the first ones to introduce that, and if you go through it, it takes a bit of understanding. Non-trivial to understand that. But this is the sad part about it. They cannot do it with a delta here. With one source, They need the fact that ax is non-zero because somewhere along the line they will divide by this. Okay, that's going to be important. It's non-zero, it's a non-zero layer. They'll divide and do some tricks. And they take notice that Q always was independent of time. This is really crucial. They make full use of that. And without it, you can't do it. So the Q is independent of time. Right? So I want you to leave with that this is really a famous result. It's a breakthrough, but breakthrough was in 81. So it's how many years now? 19 to 33 years since. Right? And the problem that I said was already known then, it's not done. Okay. Thank you very much. Sorry? So I'm sorry, some of you came to listen for Carleman estimates, right? And I was falling behind, and some of the speakers one speaker's cancelled next week. So I moved Carleman estimates to next week. All right, I'll give one talk. I'll talk about Carleman estimates and again only an outline and how it was used for this problem. I'll see if I can do it. It's not trivial, it'll take some time to do it, but I'll try. Sorry. Well,